Assalamu alaikum students. I hope all of you are doing great and preparing for midterm exam. In the previous lectures, we have studied design of finite state machines. We have designed a mood type finite state machine as well as Miller type finite state machine. Today, we are going to start another exciting topic related to sequential machines, which is about state reduction and equivalent states. If you have a state transition graph that represents a sequential machine, you can reduce the number of states in state transition graph. Generally, for every finite state machine, there is a unique equivalent machine that is minimal. So, let us start our today's topic. For example, you have a finite state machine whose state transition graph is given here. Today your task is to reduce this state transition graph or number of states. You have to reduce the number of states in this transition graph. In this graph there are some states which are equivalent and you have to identify them. So let us start. Now first let us draw its state transition table from the state transition graph. From this state transition graph you have present states, which are S0, S1, S2, S3, S4, S5, S6 and S7. So your next states are when x is equal to 0 or your input is equal to 0 and when your input is equal to 1. So from here, when you apply 0, you get 0 output and you move to state S6. And S0, when you apply 1, you move to state S3. Similarly, we can fill the remaining entries of this state transition table. This is S3, S4, this is S7, S2, S7, this is S2, this is S0, this is S1, this is S4, this is S3. And these are your outputs when x or input is equal to 0 and when n input is equal to 1. These are your outputs. So from here, when you apply 0, you get 0, and when you apply 1, your output is again 0. So you can fill the remaining entries. Here you have 1, 1, 1, and all other entries have zeros. So this is state transition table for this state transition graph. Now your task is to reduce the number of states in this state transition graph or try to find the minimal equivalent finite state machine. So the first step basically is you have to check all these rows or you have to check the outputs. Two states of a sequential machine are equivalent. This is the symbol of an equivalent. So two states of a sequential machine are equivalent if they have same output sequence for all possible input sequences. So here you can see this row and this row and this row. All these three rows have same outputs. Similarly, the last four rows and the first row, they have same outputs. When you have successfully identified the outputs or same outputs, you have to do two things, or you have to proceed in two steps. The first step is simple. The second step needs some extra work. So in the first step, you have to identify those rows which have same entries. So here your output are same and their next states are also same. Whereas if you compare this S5 and S6, their outputs are same but their next states are not same. So your two states will be equivalent if their next states are equivalent as well as their outputs are equivalent. So these two states are equivalent and you can delete one row. So as also mentioned in the state transition graph, S4 and S5 are equivalent. You can delete this state S5. After deleting this row or equivalent state, which you can represent it like this, S4 is equivalent to S5. After deleting this row S5 or state S5, you have to check the remaining state transition table and check is there any dependence of these present states on next states. So here you can see in this state S2, when you apply 1, your next state is S5, but you have deleted this S5. So I am removing this S5, and because this S5 is equivalent to S4, I am writing here S4. So after removing this row S5, your equivalent state transition table will look like this. Now you have present state S0, S1, S2, S3, S4, S6 and S7. Here you have next states when x is equal to 0 and x is equal to 1. These are your next states. So this is S6, this is S3, this is S1, this is S6, this is S2, this is S7, again S7, there you have S0, this is S4, this is S3, S2, S1, S3, and here you have S4, and your outputs are x is equal to 0 and x is equal to 1. Here you have all zeros. Here you have 0, 1, 1, 1, 0, 0, 0. Now if you compare this table from this original table, your one row is reduced, your one state has been removed. Now there is no row in this table, in the state transition table, which have same entries, but you can observe that these three rows have equal outputs, whereas last three rows and first row have same outputs. So these states can be equivalent, but you have to check them further. So how can we check them? So in order to determine the equivalent states in the state transition table, we have to use a triangular array. We have to develop a triangular array, and from the triangular array we can find out the equivalent states in this state transition table or in this state transition graph. So let us draw our triangular array. So here you have S2, S3, S4, S6, S7. Here you have S0, S1, S2, S3, S4 and S6. So this is your triangular array. Now let us fill this triangular array. In order to fill them, you have to check state by state. For example, here this is S0 and this is S1. Their outputs are different. So S0 and S1, they cannot be equivalent. So similarly, this S0 and S3, S2, they have also different outputs. They cannot be equivalent. Now here S0 and S3, they have also different outputs. They cannot be equivalent. Here you have 0 0, whereas here you have 0 1. So S0 and S3, S0 and S3, these states cannot be equivalent. Now come to the state S4. Here this S4 and S0, they have same outputs. They can be equivalent, but right now we are not sure. We have to do some work to find out whether they are equivalent or not. That's why we are filling this triangular array. So at S0 and S4, these two states can only be equivalent. These two states can only be equivalent if S7 and S6, they are equivalent. S6 and X7 pair, if they are equivalent, and S2 and S3, S2 and S3, they are equivalent, only then we can say S4 and S0 are equivalent. But right now we are not sure whether they are equivalent or not. If they are equivalent, then S0 and S4 will be equivalent. Now come to S6 and S0. Here this is S0, this is S6. They have same outputs, 0 0 and 0 0. They have same outputs. These two states can be equivalent if this S0 and S6, which are under observation, if they are equivalent, or S1 and S3, they are equivalent. So S0 and S6 will be equivalent if S1 and S3 are equivalent. Now come to the S7. Here S7 has also same output 0 0 and 0 0. These two states will be equivalent if S6 and S4 are equivalent, and S3 and S3 are equivalent, which are actually equivalent because S3 is equivalent to S3. So I am not writing here. I am only writing S4 and S6. S3 is equivalent to S3. So if S6 and S4 states are equivalent, only then S0 and S7 will be equivalent. Now come to this row. Now here this is S1 and S2. You can see S1 and S2, they have same outputs. This S1 and S2 can be equivalent only if this S4 and S6 are equivalent. S4 and S6 are equivalent. Similarly, this S1 and S3, S1 and S3, they have same outputs. They can be equivalent if S1 and S7 are equivalent, and S6 and S3 are equivalent. Now come to S1 and S4. Here S1 and S4, they have different outputs, so they cannot be equivalent. Similarly, S1 and S6 cannot be equivalent, and S1 and S7 cannot be equivalent because they have different outputs. Now come to the S2 and S3. This is S2 and this is S3. They have same outputs. So these states can be equivalent only if S2 and S7 are equivalent and S4 and S3 are equivalent. Whereas this S2 and S4, S2 and S4 cannot be equivalent because they don't have same outputs. Same is the case for S6 and S7. Now come to the S3 and S4. Here you can see this S3 and S4, they have different outputs. These states cannot be equivalent. As you can see for S3 and S7, S3 and S7, the outputs are different. So these states cannot be equivalent. Now come to the S4 and S6. This is S4 and this is S6. Here the outputs are same. So these two states can be equivalent if this S0 and S7 are equivalent, and S2 and S1 are equivalent. Similarly, for S4 and S7, outputs are same. These states can be equivalent if this S4 and S7 are same, which are under observation. So I am not writing here. And for these states, when input is 1, S3 and S2 are equivalent. Now come to this last state, S6, and we can only compare it with S7. So S6 and S7, they have same outputs. They can be equivalent only if this S0 and S4 are equivalent, and S1 and S3 are equivalent. S1 and S3 are equivalent. Now your triangular array is complete. Let us analyze our triangular array further. Here the next thing that you have to do is you have to remove some entries in which these pairs are not possible. For example, Here you can see this S6 and S7. S6 and X7, we are not sure about it whether they are equivalent or not, but here about this S1 and S7, which is here S1 and S7, here we have cross, so we are sure that these states cannot be equivalent. So if these two states S1 and S7 cannot be equivalent, then this pair cannot be equivalent. If this pair cannot be equivalent, then this S1 and S3 cannot be equivalent. Similarly, here you can observe that we have S4 and S3. S4 and S3, here you can see you have a cross here. S4 and S3 cannot be equivalent, so this pair cannot be equivalent. If this pair cannot be equivalent, this S3 and S2 cannot be equivalent. Let us see this S4 and S6. Here S4 and S6, we are not sure about it. That's why we can't say whether this S2 and S1 are equivalent. Now come to row S4. Here S6 and S7. Let us see S6 and 7. Here S6 and S7, we are not sure whether they are equivalent or not, but let us check S3 and S2. Here this S2 and S3, we have marked it that these S2 and S3 cannot be equivalent. So this S2 and S3 cannot be equivalent. If this S2 and S3 cannot be equivalent, so S0 and S4 cannot be equivalent. Similarly, let us check this S1 and S3. You can check here S1 and S3. We have marked that these two states S1 and S3 cannot be equivalent, so this pair cannot be equivalent. If this pair cannot be equivalent, S0 and S6 cannot be equivalent. Now come to this S4 and S6. Here S4 and S6, we can't say anything about it, so I am not removing it. Now come to this row. Here S0 and S7. Here at S0 and S7, we have this pair, and we can't say whether S0 and S7 are equivalent because we don't have a cross here. But for this S2 and S1, and for S2 and S1, we are also not sure about it whether these S1 and S2 are equivalent, so we are not putting a cross here. Let us check this S2 and S3. For this S2 and S3, because these two states cannot be equivalent, this pair cannot be equivalent. If this pair cannot be equivalent, S4 and S7 cannot be equivalent. So I am putting another cross here. Let us check this last box or last entry of this triangular table. Here S0 and S4, we have S0 and S4, we have put a cross here. These two states cannot be equivalent. Same is the case with S1 and S3. So these two states S7 and S6 cannot be equivalent. So from here, your simplified triangular array can be developed again. S0, S1, S2, S3, S4, S6. So here you have crosses. These states cannot be equivalent. Whereas here you have S6 and S4. Here you have S6, S4. Here you have S7, S0, and S2, S1. And here you have crosses. As you can see in this triangular array, you cannot remove other entries in this triangular array. Once you are finished with this triangular array, the remaining labeled entries represent equivalent states. Let me repeat. The remaining labeled entries represent equivalent states of your transition graph. So, S0 and S2 are equivalent. Similarly, S0 and S7 are equivalent states. Lastly, S4 and S6 are equivalent states. S4 and S6 are equivalent states. And previously we have removed this row S5. That means S4 and S5 are equivalent states. So S4 and S5 are equivalent states. So these are your equivalent states. Now let us delete more entries from the state transition table, which you have already reduced by one row. You have removed S5. Now let us remove other equivalent states. As you can see, S0 and S7 are equivalent. I am deleting this S0. Once you have deleted this row, you have to make sure that this S0 is not present in your state transition table. So as you can see, this S0 is present here. So you have to replace it with S7. So here you have S7. Similarly, I am deleting S1. S1 is equivalent to S2. Now let us check whether there is S1 here. You can see we have S1 here. So this S1 can be replaced with S2. So I am writing here S2. Now here this S4 and S6 are equivalent. Let me delete this S6, and I have already removed S5. Let me check, is there any S6 in the remaining part of state transition table? Here you do not have any S6. Now you have fully reduced your state transition table. Now let us redraw our reduced state transition table. In the reduced state transition table, we have S2, S3, S4 and S7 only. These are your present states, and when input is equal to 0 and input is equal to 1, these are your next states, whereas your outputs are here. So here S2, you are moving to S2, and here you have S4. Here you have S7 and S3, S7 and S3. Here you have S7 and S2, and here you have S4 and S3. Whereas your outputs are here 0 0 0 0, and here you have 1 1 0 0, 1 1 0 0. So this is your reduced state transition table, which has only 4 states. Now let us draw our reduced state transition graph from this reduced state transition table. Here you have 4 states: S2, S4, S3 and S7. At S2, when you apply 0, your output is 0. You move to S2, your output is 0. And when you apply 1, you move to S4 and your output is 1. Now at S4, when you apply 0, you move to S7 and your output is 0. And when you at S4 and if you apply 1, you move to S2 and your output is 0. Now at S7, if you apply 0, you move to S4, your output is 0. And when you apply 1, you move to S3 and your output is 0. And when you are at S3, for 0 you move to S7 and your output is 0. And when you apply 1, you remain at S3 and your output is 1. So this is your reduced state transition graph. If you compare this reduced state transition graph with the original state transition graph, which had 8 states, S0 to S7, we have only 4 states here. In the original state transition graph, you need at least 3 bits for state registers in your sequential machine, whereas here you require only 2 bits. In this case, your state register requires only 2 bits. As we have reduced the number of bits in your state registers, your sequential machine circuitry is reduced. In other words, cost of your sequential machine is reduced. So state reduction is very important. It can save your money. I hope you have understood the procedure of state reduction. This is end of today's lecture. If you have any question, you can ask me via an email. My email address is given. See you in the next lecture. Thank you.